So what do we observe is, well, relative to the table, two objects have been moving. This piece of paper, this card, and again, the physical nature of the objects doesn't matter. We can just count them, first, second, third, and what we see here is the displacement of this card relative to this piece of paper, which doesn't depend on the motion or the absence of the motion of the paper relative to anything else. Well, together with the displacement of this object paper relative to the table, give the total displacement of this card relative to the table. Now, this is the easiest situation when everything points in the same direction. So naturally, we need to take a look at a case when yes?
So the displacement relative to the table, and the displacement of the cart relative to the paper?
This question is simultaneously good and have no meaning. Technically, according to an official definition, a displacement is a vector. So when you want to compare a displacement and another displacement, you should be saying magnitude or length or absolute value, and like longer or shorter. And if you just say a displacement, in that case, we technically cannot answer the question, but we can assume that you meant length. And in that case, in this particular situation, you can see from the picture that the magnitude of the displacement of the cart relative to the table is greater than the magnitude of the displacement of the cart relative to the paper. Natural question is, by the way, for sale. Natural question is it always the case? We don't know until we investigate all options or go to the math class and start doing the mathematics about vectors. So I prefer first approach, just an experiment with the same card. See, people who designed this room, they didn't think of a relatively large person, because simultaneously I'm showing it to you and I'm blocking it for you. Anyway, so what I want to do, I want to fit it in here. Well, let's try this. So, okay. This is the starting point of this card relative to this piece of paper and relative to the table at the same time. So when I press the button, it will travel to the left relative to you. And I'm going to now pull this paper again in the same direction. And let's see what's going to happen. Move. Move. It's your fault. That's why I have a backup. And a backup for the backup. Let's see if it... They just don't want to move. Okay. Okay, and this is the displacement of this card relative to this piece of paper, right? So now, and because this piece of paper represents like a lake, the same displacement we observe relative to the table. Oh, okay. So what do we see now? Oh. I moved the wrong one. Go ahead. It's not even Friday yet. All right. Well, it's supposed to be practically. Well, anyway, it's supposed to be practically here, right? Maybe battery is dying. So, markers. Actually. What's what? Well, here, so if it starts here and it ends here relative to the ground, this is, that's number 3, right? We called it number 3, number 2, number 1. This arrow represents the displacement of this cart relative to the ground. And this was and still is the displacement of this cart relative to this paper. But the paper was traveling to the right, and this represents the displacement of the paper, object number 2, relative to the object number 1. This is how it moved. Yeah. For example, you can look at this red object. It was moving with the paper. If you imagine a river, you can imagine this is a raft in a river. Raft has no sail, raft has no engine, raft just travels with the stream. So the speed of the raft relative to the shore is basically this speed of the stream of water relative to the shore. And now, according to tail to a head rule, R32 plus R21 still equals R31. The equation hasn't changed. We just have to keep in mind that we use vectors here. This is a tail to a head rule. One arrow plus another arrow. This is the initial, this is the final kind of location for this vector addition walk. And when we use vectors, the equation which relates those displacements is the same. It's the same equation. However, now, when we want to relate distances, magnitudes, numbers, situation is different. Now, if we want to use magnitudes, we should say that magnitude of this displacement plus magnitude of this displacement will be equal to the magnitude of this displacement. Magnitudes, absolute value, length. So if I want to calculate the magnitude of this final displacement of the third object relative to the ground, that actually will be the difference, because I have to take this and subtract this to get this magnitude. Or I can solve this equation. What did I do? That's 3,2. 3,1 plus 2,1, 3,2 in magnitudes. So 3,1 will be equal to magnitude of 3,2 minus magnitude of 2,1. So when you So this is an important, again, example of well, how language matters. Language matters. When we say a word like displacement, every time we must be able to say, what do we mean? Do we mean an action? Do we mean a vector? Or do we mean the length of that vector? Depending on what we mean, our equations look differently. But most textbooks, when they say word displacement, they mean magnitude. In this class, when we say word displacement, we mean vector. So displacement over time is velocity. If where is it here? If the equation which relates displacement is the same, and it is the same, equation for velocities, of course, is the same. So the law of relative velocities doesn't depend on the actual situation. It is the same. Well, question. This question refers to the picture we saw. A passenger was walking inside the airplane, which was flying above the ground. So if anybody want to open museum or learning physics, too late. Bless you. Well, picture worth 1,000 words. So people who draw a picture, that's what we call participating. People who don't draw a picture, that's what we call being present. And the picture is, well, to which situation the picture is similar, to the first one or to the second one? The first situation, when everything was pointing in the same direction. Second situation, when displacement were opposite. So one displacement points west, another points east. So that's the case number 2. That's not the case number 1. And we have the ground, the airplane, and the passenger inside. Right? Now, the airplane travels east. Now, when we say travels east, and we draw an arrow, that arrow must represent a specific velocity of a specific object relative to a specific object. So this is the velocity of the plane relative to the ground. The plane has moved from here to here relative to the ground, 300 meters. What is it? That's the displacement of the plane relative to the ground. And well, I'm just giving you time. Please keep entering your answer. And the person walks inside. Inside the plane means there is an observer on a plane, another guy who's watching. There is always an observer. And when we say relative to the ground, we mean as seen from the ground by a person who's looking, not moving, sitting on the ground and looking at whatever happening. So relative to that observer, that's what relative to the ground means. And here, relative to the plane means relative to an observer which is on the plane. So relative to this person, this is an observer, and this is the passenger. The passenger walks west. And this arrow should represent now the velocity of the passenger, P, relative to the plane, big P. Yeah. And the displacement here is supposed to be the displacement of the passenger relative to the plane. And we could use the general equation, or we can write an equation for this specific situation. The displacement of the passenger relative to the ground should be equal to the displacement of the passenger relative to the plane plus displacement of the plane relative to the ground. This equation is absolutely identical to the equation we wrote yesterday. You just need to remember all those variables of vectors. So what can we do? Well, this is what we can do. We know how to add vectors. The displacement of the plane relative to the ground, this arrow, is a long arrow which points to the right. And the displacement of the passenger relative to the plane is a short arrow which points to the left. So now we add them up together. 1, 2, exactly like we did in the second example. And now we can draw the arrow which represents the displacement of the passenger relative to the ground. It points east. And of course, it is a little bit shorter than the displacement of the plane relative to the ground. By how much? By 4 meters. Any questions? Well, so this is the problem we started. I'm going to draw my picture. You're going to draw your picture. This situation includes 2 parts. Round trip means traveling east first and then back. So on its way east, what's happening? Distance traveled is equal to 112 kilometers. Well, let's convert it into meters because I can see the speed is in meters per second. So meters, that's distance traveled. Now, so speed of the cloud relative to the pilot. That means speed of the pilot relative to the cloud will be equal to the same number. But if we talk about velocity, well, in general, if we have any 2 objects, a plane and a cloud. I don't know, why is it a plane? No, this is a plane. A plane and a cloud. So we can call them 1 and 2. So velocity of the plane relative to the cloud has the same magnitude but opposite direction as velocity of the cloud relative to the plane. When we say relative, again, we imagine a person sitting there and looking at another object. So if cloud had eyes, and a ray gun to measure speed of the plane, that would have been 300 meters per second. But if a pilot can measure speed of the cloud, that would have been 300 meters per second, but relative to each other, they travel in opposite direction. So the velocity, well, because the plane travels east, the velocity of the plane relative to the cloud is 300 meters per second. And on its way east, the velocity points east. Now, the wind also blows east, so this is the velocity of the cloud relative to the ground. It's been measured by meteorologists, and so that's what we know about the first half of the trip. And, well, let's draw a picture. It's a round trip, so it travels back exactly the same distance, right? And nothing happens to the wind. It still blows east, so it doesn't change this. Cloud, ground. But, of course, now the plane flies back west, so this will be now the velocity of the plane relative to the cloud. Still same number. This number is fixed by the engines of the plane. So this is the only difference. But from a perspective of a person on the ground, the velocity of the plane relative to the ground will be different. Now, the equation in each situation which relates velocities is exactly the same, because the law doesn't depend on the nature of the situation. It's the same law, 3.1 equals velocity 3.2 plus velocity 2.3. But the application of this law will give us some difference, because, well, the velocity of the plane relative to the air, relative to the cloud, has different directions. So I can immediately actually tell just what will be the speed, the magnitude of velocity, the speed in the first case relative to the ground. That will be 300 plus 220, 320 meters per second. And if we know that, and we know distance, we can calculate time, right? How? Speed equals distance over time. Time equals distance over speed. So time east will be equal to distance over speed. Distance, well, 11 over 320. What's going to be the difference in the second situation? Well, in terms of vectors, the equation is the same, but if we go from vectors to magnitudes, now we know we have to subtract actual values. So the magnitude of the velocity of the plane relative to the ground, which we call speed of the plane relative to the ground, now will be equal to 300 minus 20, because the air dragged it back a little. So that's going to be 280. And of course, now we can calculate time west, which is same distance over, how many zeros? Too many zeros. Over 280. And if we add these two numbers, we get the total time for the whole trip. Just an illustration how direction might affect the speed. The equation for velocities, again, is exactly the same. But the transition from vectors to numbers brings some difference. Any questions? Please. Please ask a question. Yes? You're saved. if you want to use numbers, I would suggest using components. It's more accurate and less risk to make a mistake. So this is vector number 1. Well, let's call him the plane is the object number 3, the ground is the object number 1, the cloud is the object number 2. The equation which relates velocity is always the same. This is 3, 2, and this is 2, 1. So what we know about vectors, they have components. Components, well, in this situation, very simple. Relative to the x-axis, the x component of what we're looking for should be equal to the x component of this velocity plus the x component of that velocity. But in numbers, see, this vector points opposite to positive x direction, which means the component is negative. And this vector points in positive x direction, which means the component is positive. So the x component of the velocity of the plane relative to the ground is negative, of course, because it travels to the left. But the magnitude of this absolute value, what we call speed, is just a positive number. When you're not sure how to apply tail to a head rule, how to add vectors geometrically, you can always switch to components. Components never lie. People do. Components don't. So that's the answer. And now we're going to talk about situation when velocities are angled toward each other. Here we have a standard case of well, a boat traveling across a river. So let's first take a look at this case in general. So this is the boat. This is the river. Okay, let's see. Okay. So this is the case number 1. That would have been case number 2. So if we want to cross the river, the boat might be directed at some angle relative to the stream. And what's going to happen now? Okay, let's see if angle is not too large. Okay, so here. This is the displacement of this boat relative to the river or lake. Doesn't matter, because as we know, the motion or the absence of this motion doesn't affect this displacement. So now what's going to happen if it's not a lake, a river? So, okay. I have to go back, and this is what I need. I need because I need to know the starting point. Okay, here. That's all we need. So that arrow represents the displacement of this boat relative to the water. So if this is number 3, water is object number 2, the ground is object number 1. So this is the displacement 3, 2 of the boat relative to the river. Now, again, if this is a river and we're looking at the raft which travels with the river, this is the displacement of that raft, which is the displacement of the water relative to the shore during this time interval. So that's water relative to ground. And the full displacement of this boat relative to the ground is this one. R31. We can see again that the displacements related by exactly the same equation. Delta R31 equals delta R32 plus delta R21. It is the same equation. We saw it yesterday. It hasn't changed. It cannot change. Technically, we wouldn't even need to do all this stuff because the equation is the same. But it helps to visualize what might be happening. And what might be happening? Well, we have two options, standard options. When we aim the boat straight across, aiming means directing, pointing. And in this situation, narrow. Okay, we'll see. In this situation, because of the stream, it lands not across, it lands down the stream. And another situation, if we aim up the stream, now technically depending on how fast the stream is, it can land at different locations anywhere. But for every situation, we always can write this equation. And displacement over time is velocity, so we can always write the law of relative velocities and apply it accordingly. And that's what we're going to do. Again, technically, this is nothing new. This is application of a well-established and learned theory to different, slightly different situation. The projectile motion, which we learned yesterday, is an actual two-dimensional motion. This motion is not two-dimensional. You saw the cart was traveling along a straight line. However, turns out in many situations, to understand what's happening, we can pretend that this motion actually two-dimensional. We can select two axes conveniently. One is parallel to the shore, so this parallel to the stream, and second is perpendicular. And in that case, when we use vector components, all calculations become very, very clear and simple. All right, so first, I'm going to ask you a question. What do you think? How should we aim the boat to cross the river by the shortest distance? Well, if a picture worth 1,000 words, 4 pictures worth 4,000 words. And that's what you're supposed to be doing, drawing 4 pictures, one for each case. Like this, for example. What does it mean? So you have, what happened? You have the river. Let's say the stream goes to the left. You are here, and your landing point is somewhere upstream. Well, in a lake, or without any stream, if you aim your boat straight across, you would land straight across. Upstream means you landed somewhere here. So in this situation, relative to a person watching from the ground how the boat moves, this would be the displacement. Now, next situation, you start here and you land at the point directly across. Directly across means this. So that's the stream, that's an observer on the ground looking at you, your friend or enemy. And that's what that observer observes. Now, you aim the boat directly across, but the stream drags you down. So this is something like this. And the last situation, you start here and you drag down even more. And if you look at these four pictures, well, which picture represents a situation when you travel the shortest distance? Which picture represents a case of the shortest distance? Number 1, 2, 3, or 4? 2, number 2. It's not a tricky question. You can just see it because you know, well, your brain can estimate the length and compare. So all other options are longer, 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 even longer. So this case represents the shortest distance. So again, this is your displacement or displacement of the boat relative to the ground. It's very important to understand what it is. In order to travel that way, you can't aim the boat perpendicular to the shore or to the stream, because that would have been this case or this case. So if you aim straight, if you aim directly across, that would have been the velocity of the boat relative to water. The stream drags you down. So you have to aim your boat differently. These words, angled, aimed, point, directed, they describe the orientation of the boat. The speed of the boat doesn't depend on the orientation. The speed is a fixed number because it depends only on the engine, on the properties. But the orientation, the velocity, depends on how you aim it. So the question is now, how do you aim? You have to aim your boat slightly, well, we don't know exactly how much, but up the stream. This is supposed to be the velocity of the boat relative to water. Like in our example, with the river dragging it down, that should be the velocity of the water or river relative to the ground. And these, well, and if this arrow, this long arrow, represents the displacement of the boat relative to the ground, that means the velocity of the boat relative to the ground should point in the same direction, because velocity is displacement over time. So these are vectors we need to relate. How? Well, of course, we have to write the law of relative velocities. So that's the answer. And we just have to solve a specific problem to finish this type of a strategy. So again, same picture. We start here. We aim the boat like that. This arrow should represent the velocity of the boat relative to water. So an observer on the ground watching how you travel relative to the observer, you travel straight across. That's the velocity of the boat relative to the ground. And there's velocity of the stream relative to the ground, velocity of water relative to the ground. That is the velocity of a raft or leaf which flows with the stream. So if this guy is looking at that raft or leaf and measures velocity, that will be this number. Now, the law of relative velocity says velocity of the boat relative to the ground should be equal to the velocity of the boat relative to water plus velocity of water relative to the ground. So now that gives me 5 plus 3, 8. When I stop talking and walking around, that means I'm waiting for something. And what do you think I'm waiting for? What do you think I'm waiting for right now? Anybody? I'm not very often here in the back. So what do you think is happening? Good? Any questions? No questions? No suggestions? No opinions? Anybody? Yes? So you're saying I made a mistake? You sure? You're right. I made a mistake. Like many people make similar mistake. That's a very wrong way to do it. What's wrong with that? Anybody? What is wrong with this type of a calculation? Yes? So I treated vectors as they would have been numbers, and that's wrong. It's like someone calls you a wrong name. You get angry. So I made a mistake. Each variable in this equation is not a number. Why did I make that mistake? Because I was lazy. I didn't put this sign which says it is a vector, it is a vector, it is a vector. If I would put this sign, I would know that I cannot do this because this is wrong. So what? We made a mistake. We figured it out. Now we can fix it, right? So fix it. Spend, I don't know, a minute or two and try to calculate the magnitude of the velocity of the boat relative to the ground. That's an unknown number. This number, bless you, 3 meters per second, represents the magnitude of the velocity of the water relative to the ground. 3 meters per second. It says in a lake, your boat would have been traveling at 5. In a lake, that is a clue that this number represents the velocity of the boat relative to water. The only missing number is the velocity of the boat relative to the ground. And the relationship between these velocities is provided by the law of relative velocities. However, we cannot treat velocities as numbers because they are not. But you know how to treat them as vectors because it's a vector addition situation. You just have to add two vectors to get the third one and figure out the magnitude of the third one. And in order to do that, you have to draw a picture which clearly shows three arrows, the arrow number 1, the arrow number 2, and after that, the arrow number 3, the one which we are looking for. Not today, but soon, I'm going to ask you to take a picture of your picture and email it to me. So be prepared, it will happen. You may need a cell phone, tablet, or a friend with a cell phone or a tablet. If you don't have friends yet, start looking. So, yes?
Problem doesn't necessarily direction that the vector should be going.
Theoretically, when we have no information about direction, we have to analyze all possible options, all of them, and see if it makes any difference. You can choose your own option. You don't have to stick to mine. Okay? So as long as anybody has a number, just show me you have a number. Say, okay, thank you, thank you, thank you, thank you. Oh, perfect. So, I'm going to add an extra slide. So all I need is just vectors. And so this is the velocity of water relative to the ground. My choice, doesn't have to be yours as well. And the magnitude equals 3. My short memory is short. 3 meters per second. And this is how we aim the boat relative to water. And the magnitude of this, 5 meters per second. Now, we know that the velocity of the boat relative to the ground should point like this, perpendicularly to the stream, boat, ground. But we don't know the magnitude of that. But what we do know is that the law of relative velocities relates these three vectors. Hence, this arrow plus this arrow should give us this arrow. Well, I just flipped the sides. Or we now can complete the tail to a head rule. Bless you. This plus this equals that. And now we can just redraw the triangle. In this triangle, the long side equals 5. The horizontal short side equals 3. And that's what we're looking for. And what's the answer? This number. Yeah, so what's the number? I heard you. Thank you. What's your number? You see? You lost 30 seconds. But if you would remember that it's a 3, 4, 5 triangle, you could have saved those 30 seconds. That's a 3, 4, 5 triangle. So the answer is 4. Sometimes keeping some things in the memory saves time. Sometimes time matters, you know when, right? So that's the speed of the boat relative to the ground. So if we have a river and there's an observer looking how the boat is traveling, the boat actually angled like this, but travels like that. Yeah? And I think we know the distance between, 100 meters wide. So if we know the speed, we can calculate, and we know the distance, 100 meters. We can calculate time it takes to cross the river. So what people confused sometimes is, what number do we have to use to relate this number, 100, and time? Well, here, pretending that it's two-dimensional motion might be helpful. So this arrow represents the velocity of the boat relative to water, but relative to these two x and y axes, it has two components, vx, I call it y, vy, and vx. And like in the case of a projectile motion, we can see, well, first of all, they don't interfere, but we can see this component has nothing to do to crossing. This component is responsible for, we can call it horizontal left-right motion. Only this component is responsible for traveling across, and that component equals 4 because we found it. It is equal to the magnitude of the speed. So if we write an equation which relates speed, distance, and time, most important part is to remember that all variables in this equation are supposed to be related to the same origin. You cannot use velocity relative to water and use time relative to ground. If you do that, that will be wrong. Don't do things which are wrong. So you need velocity of the boat relative to ground and distance measured from the ground. And time, of course, will be equal to 100 over 4 25 seconds. We use International System of Units. Any questions? All right, now I'm going to go faster. So please tell me what you think. In this situation, most probably you just have to follow your guts. How would you aim the boat now if you want to cross the river as fast as possible? Even if the path is longer, you just want to get it as quick as possible. And of course, we can investigate all the situations. What is important, that the speed of the boat relative to water doesn't depend on the orientation of the boat. It depends only on the engine you're using. So you can aim your boat differently. You can aim your boat like this, or like this, or like this. The length of each arrow should be the same. The length magnitude is speed, right? So all possible orientations described by a semicircle. So, but only one orientation gives you fastest trip. Which one? Well, again, in this situation, it's handy convenient to pretend that the motion is two-dimensional. So let's say I aim my boat like this. This is the velocity of the boat relative to water. This velocity has two components, Vx and Vy. And the y component, or we could call it vertical. Yeah, but it's not related to actual vertical, but on the screen it's vertical. The y component has nothing to do to crossing. Only the x component matters. By changing the orientation, we do not change the length of this arrow, but we change this component. If I make the velocity more and more parallel, this component shrinks. If I make it more and more perpendicular, this component increases, but then it decreases again. So, same equation can be written in components. In components, this should be equal to distance over time, or time should be equal to distance over the x component. If I want to decrease the time, what should I do to the x component? Increase it, makes it as large as possible. So which of these arrows would give me the longest x component? This one. It doesn't have y component at all. So this is how we should aim the boat in order to travel as fast as possible, but because of the stream, we will land somewhere down the stream. We will not be able to land across, because that would have been a different case, shortest path. This is the quickest trip, different situations. So that's the answer, point directly across. This is, well, picture, and this demonstrates the fact that river drags you down. This is how much distance you will be dragged down relative to your initial location down the stream. And of course, now we just need to solve a problem. The river, 1,800 meters wide. Velocity of the boat relative to water, 4 meters per second. And the stream travels at 2 meters per second. Okay, got it. So, want to be consistent with this picture. So the stream points to the right in this situation. This arrow represents the velocity of the boat. No, sorry. The velocity of the river, stream, water relative to ground, shores, tree on the ground. And we want to cross it as fast as possible. So that's how we aim the boat. This arrow represents the velocity of the boat relative to water. And as we know, the velocity of the boat relative to water plus velocity of water relative to ground equals velocity of boat relative to the ground. These are vectors. So this plus this equals what? This arrow represents the velocity of the boat relative to the ground. And well, so the landing point will be somewhere there. This is how much it will be dragged down the stream. And well, again, we have a triangle. In this triangle, what do we know? We know this 2 meters per second. And we know this 4. This is not a 3, 4, 5 triangle. I don't know why. But still we can use Pythagorean theorem to calculate this speed of the boat relative to the ground, square root of 2 squared plus 4 squared. And well, if I know how wide the river is, I can calculate again how much time would it take to travel across. But in order to do that, which number should I use? Well, again, it is handy, convenient to pretend the motion is two-dimensional. So we need to relate length with this component. This component is equal to 4. So but now if we know time, we can calculate this distance, delta x. We just need to use the x component, which is 2. Delta x will be equal to Vx times time. We can find the displacement. The displacement is not equal to the width of the river, is not equal to horizontal displacement. It is equal to the length of this arrow. That's beginning of the trip, that's the end, that's total displacement. So how can we do that? Well, if we know this and we know this, we can use Pythagorean theorem. There's another option, because we know this speed times time, and we know time gives displacement. So again, we have more ways to solve this problem. And I've got slides. And this is the summary. I have 3 slides with the summary for different orientations. This is the case when the river travels horizontally-ish. This is the case when the river travels vertically. It doesn't affect physics at all. When we draw arrows, we just must be able to say the exact meaning of each arrow. That's it. The velocity of the boat relative to the ground is this. The velocity of the boat relative to the water is that. The velocity of water relative to the ground is this. Then we draw a triangle, and the triangle allows to calculate anything we want to. Any questions? We're done with velocities, displacements, and we start the new topic, dynamics. We're going to talk about forces. And this is not anything new, as you can imagine. Everything we're going to learn today, tomorrow, next week, hundreds of years ago would give you a PhD. Now, it will give you an A, hopefully. So forces. We know a lot of information about forces just from our everyday experience. We know many forces. For example, we know that force of gravity exists. It is acting on anything which is close to relatively heavy object. And force of gravity pulls on everything straight down. But so there are forces which, well, that's a pull, that's a push. There are forces which don't require objects to touch each other, gravity, for example. But however, in mechanics, most forces are contact forces. Two objects must touch each other. And when that happens, they interact. For example, My finger touching this plate of the scale. Well, the scale touches my finger. Interaction always happening between two objects. And if I exert a force on the scale exerts a force on me. And this force has no name. We call it applied force. Force in a string, in a cable, we call it the force of tension. What is the difference between force of tension and just applied force? Where is it? Here. My favorite textbook. With something stiff, I can push. I cannot push with a string. So tension can only pull. Force of tension always points away from an object in the string. Now, we know with the force of friction, right? You give it a push, it stops. Why? Friction. We also know the force which keeps things. For example, this table prevents this block from falling down. This type of force has a name, normal force. And the normal doesn't mean all other forces not normal or abnormal. Normal in mathematics and in physics means perpendicular. So the same block might sit on an inclined plane. Still, there is a force which prevents it from falling, normal force, which is perpendicular to the surface. But if I tilt the plane, oops. Which way? Here. The same surface still acting on this block prevents it from falling. But the force which we call normal has to be perpendicular to the surface. That's a part of a definition. So friction, of course, well, friction might be strong enough to prevent it from sliding, or not strong enough, it slides down. And friction always is parallel to the interface between the object and the surface, parallel to the surface. Elastic force inside a spring or a rubber cord. If you stretch it, you feel it. Yeah? Well, string, sometimes you can compress, still you feel it. Here in this scale, we have a spring, which I try to compress, and I feel it. And the compression is related to the amount of the force, to the magnitude. That's how we calibrate the scale. Well, so a list of standard forces and force of tension here. If you have a fan, it makes the cart move. Just applied force. Anything which makes something move, we can call applied. Every force has a source. That's a very important statement to remember. If a force is acting on something, something, it means there is another object which is responsible for the existence of this force. Every force has a source. Just, well, seeing it. And of course, when one object is acting on another, that object acts back. This statement has a name, the third Newton's law. And the official statement says, when two objects interact, they exert on each other forces which have the same magnitude and opposite direction and act along the same line. Mathematical description of this law is here. So in this example, swimmer, the lady, he pushes on the wall. That's a force from the lady on the wall. And because of the interaction of the third Newton's law, there is a force acting from the wall on her. And according to the law, those forces have exactly the same magnitudes, but opposite direction. And this law applies to any interaction between any two objects. Doesn't matter, big or small, heavy or light. Any two objects, when they interact, they exert forces which have the same magnitude in opposite direction. Why would the ball bounce off the table? Well, when the ball hits the table hits the ball, and that force makes it travel upward. Now, no question, don't ask it, just tell me what you think. So what's happening here? The heavy object, a crate, and two people pull on it. So strong man, not so strong boy, and they pull it strong enough so it starts moving. The question, how do you expect it would move? Which path do you think is the most natural? What do you think? Number 1, number 2, number 3, number 4, or number 5? Just tell me. You say 2. Yes, of course. So this is basically something like that. One force pushes in one direction. Second force pushes in a different direction. But if they push simultaneously, that's what we see. And this simple experiment tells us that force is not a number. It has a direction. And if it's not a number, it has a direction. It means force is a vector. And when several forces are acting simultaneously on the same object, the result depends on all forces together. Together in mathematics means what? The sum, exactly. So when many forces acting together, we need to add them up together mathematically as vectors. The result is an abstract vector, but it has a name, net force or total force. And that force, net force, total force, is responsible for whatever is happening to the object or to the system. This is a standard mathematical symbol for the word the sum. So the sum of all forces acting on an object, that's the symbol, that's the name, represents the net force. That's a definition. It is equal to the sum of all actual individual forces acting on this object. That's what it is. So far, it's just definitions, and definitions don't require understanding. There's nothing to understand. They require memorizing. This is the question I want to ask you, but that's not going to be number 6 now. That's going to be just number 5. In this example, we have an object under 3 forces acting on it. You see direction of each force. You see the magnitude of each force. Your goal is to calculate the magnitude of the net force and just press a number which represents the magnitude. Yes? Cannot hear you. Maybe things happen. Let me see what is happening on the web sign. So 30% said I was late. Thank you for your honesty. Second, third, fourth, fifth. Okay, maybe I labeled 2 questions. Yes. You should answer the question which you can answer right now. If it's 6, it's 6. I thought, doesn't matter what I thought. And I'm going to do the same thing. So this is what I like to do. 2 plus 3 plus 6 equals 11. When I stop talking and I walk, what does it mean? Or, so please, you got me. So don't do that, it's wrong. Never assume that vector can be treated as a number. Wrong. But it's an easy fix, right? So, an easy fix. Let's see your answers. Plus, the answer 11 wasn't even presented in the web assign. Okay. Yes. So, technically, this is what we're doing. This plus this plus this equals what we're looking for. I want to rearrange them. I want to do this plus this because that makes my calculation easier. Here I have 2 vectors opposite to each other, so together they give me one shorter vector. This is 6 newtons to the right, this is 2 newtons to the left, 3 newtons up. So here I have 4 newtons to the right, left, plus 3 newtons up. That gives me 5 newtons. At what angle? That's not a question, but we can immediately figure it out. Yeah. If we need to calculate this angle, we actually did it before, right? 3, 4, 5, triangle. Alpha equals inverse tangent of 3 over 4. I think it's 37. Well, that was an easy example, of course. So every time when we need to calculate net force and then use it for something else, we need to keep in mind that every force is the result of interaction. But normally we do not show those objects which are responsible for the existence of forces acting on our objects, on objects of our interest. Instead, we draw a picture which shows only forces, and that picture has a name, a free body diagrams, because it doesn't have other bodies, other objects presented. For example, picture number 1. So we have the object of our interest. And we have to use our common sense to show all forces acting on it. Well, first of all, of course, there is a force acting from the wall, which propels her. But everything is happening here on this planet must be force of gravity because of the Earth pulling down. But we also know from our common day experience there has to be a buoyant force because water pushes up. Plus, there has to be a force of resistance. And we don't need to know how to calculate or find those forces. What we need to know is they exist and act. This is a free body diagram for the first case. Case number 2. Well, when something is on the ground, we usually show the presence of the ground. The object, the car, is on the ground. Well, we know, first of all, it doesn't fall through the ground. So it has to be force of support, and that force has a name, normal. But also, it's happening on the Earth, so there is a force of gravity. Now, these two guys push two forces which point to the right, and we can see there's force of combined resistance, friction, internal friction, maybe air resistance. That completes this free body diagram. Number 3. Well, we know this example. There's one strong force in one direction, second strong force in another direction. In reality, in the actual life experience, if this is a guy and this is another guy, that means everything is happening on the ground. But this picture represents the view from above. And when we look from above, the normal force points up and the force of gravity points down. So it's not easy to draw those forces. They kind of exist, but that's what we see. There is a way around it, but not now. Here we have two objects. So the diagram should be drawn for each independently and individually. Number 1, it sits on a table. Table supports it, so it has to be normal force. And of course, must be force of gravity acting down. Of course, string pulls, and theoretically, in general, there might be some friction. Friction always opposes the motion. Now, second object hangs on a string. Well, in general, depending on many situations, the system might be at rest, or if there is no friction, they will move. At this point, it doesn't matter what might happen. So there is force of tension because of the string attached to it, and of course, force of gravity. Now, what's missing in all diagram? The labels. We have to label each force. And on the slide before, for the force of gravity, the magnitude of the force of gravity can be found by multiplying the mass of the object times g. G is 9.8 or 10, or if it's on a different planet, so different g. Well, for the normal force, people use, well, for every force, people sometimes use just F, capital F, with a subscript, normal, resistance, or no, this is resistance, and this is, I don't know, applied. Here, normal. Another standard symbol for normal force is just capital N. Yes? Can't hear you. Oh, B. Thank you. Thank you for paying attention. When time is running up, I try to speed up, and sometimes miss little things. Good catch. This is normal force. This is the buoyant force. And this is applied force number 1, applied force number 2, force of gravity, force of resistance, of friction. Here, friction, normal, gravity, tension. Another symbol, common symbol for tension is capital F with a subscript. You can choose wherever you like. For any force, any label, any symbol, it does not matter. But you need to know, if you use that letter, what you use it for. Now, in general, we have two situations. Situation number one. I'm going to do this first. Situation number one, when an object is at rest, even when forces are acting, it's not moving. We call it equilibrium. And in equilibrium, the net force must be equal to 0. And there's a situation number two, situation when the net force is not 0. And I just want to finish with this. So it's not moving. Why? Well, again, there is a force of gravity acting on it. There is normal force. And there is touching force, has no name, finger force, yeah, resistance, you can call it. And there is a applied force, which tries to propel it. So, but if I release it, it starts moving. Now, if we had a motion sensor, we could actually measure everything, velocity, acceleration, and what we could do is to figure out how those variables are related. For example, what would happen if I change the mass? If I don't change anything else but the mass, the force which pushes it doesn't change, the same, but it's heavier. If it's heavier, it is not just moving slower, it's speeding up slower. It decreases acceleration. Now, well, I can add more mass, even more visible decrease in the acceleration. So same force, but when mass goes up, the acceleration goes down. What happens if we change the force? Here I have two fans. One, you know what? Here, one fan propels it, and again, we can calculate acceleration, calculate everything, and relate force, mass, and acceleration. And now I'm not changing the mass, I'm doubling the force. And when I'm increasing the strength, doubling the force, measuring acceleration, I can see it also changes. So that's what Isaac Newton came up with. He related mass, acceleration, and the force acting on a system. And before I go, one more thing. For this system, right now, this is an external force. So this fan pushes on air, and according to the third law, air pushes back. Well, that's all time I have. Thank you.